Welcome to the deep dive. Today we're going on quite a journey. You've brought in some sources that connect a mathematical idea from 1889 to the most advanced microchips being made right now.
It really does sound like a history lesson, but I promise you the application is about as cutting edge as it gets. We're going to dig into something called Prüfer codes.
Prüfer codes.
Yeah, it's a concept from graph theory that is, and I'm not exaggerating, revolutionizing electronic design automation. EDA.
It's basically finding a mathematical shortcut to manage the billions, literally billions of connections on a modern chip.
That's the perfect way to put it. I mean, the scale is just mind-boggling. When you design a new chip, you slam right into what engineers call the curse of dimensionality.
Right.
You have this vast, sprawling web of logic gates, memory, power lines. It's all a huge multi-dimensional puzzle. And your job is to optimize everything at once, the layout, the timing, the power draw.
And if you try to map that out as a traditional graph, it just becomes unmanageable.
It becomes computationally intractable. Exactly. Right. It's a spatial challenge on a monumental scale.
So our mission for this deep dive is to unpack the tool that solves this. The brilliant translation that turns that spatial mess into a simple linear sequence.
We're basically looking for the genetic code of a microchip.
I love that. And to understand the code, we have to go all the way back to the beginning, to the pure mathematics of it all.
We do. It all starts with something called labeled trees. Back in the late 1800s, the mathematician Arthur Cayley was fascinated by a simple question. How many different ways can you connect n points without making any loops?
And that's the definition of a labeled tree, right? Every point has a unique name, and there's only one path between any two of them.
Precisely. And in 1889, Cayley came up with the formula. For n vertices, there are exactly n to the power of n minus 2 unique trees.
N to the n minus 2. So even for something small, like 10 nodes.
You're looking at 100 million unique possible structures. It just shows you the insane complexity engineers are up against.
That's an astronomical number. And just knowing how many there are doesn't help you find the best one.
Not at all. And that's where Heinz Prüfer comes in, 30 years later in 1918. He didn't just count them, he gave us a constructive proof.
Meaning he found a way to actually build each one systematically.
He established a perfect two-way translation. In math, we call it a bijection.
A bijection. Okay, so in plain English, what does that mean for us?
It means a perfect one-to-one mapping. For every single spatial tree structure that exists, there is one and only one unique sequential code. And for every code, there's only one tree.
Like a perfect dictionary.
A perfect dictionary. You translate the complex physical design into a simple string of integers, and you can translate it back perfectly with zero loss of information.
And that is the whole magic trick. Taking something spatial and making it linear. And this code it's really compact too. For a tree with n nodes, the code is always n minus 2 elements long.
It boils the entire structure down to its absolute essence.
Okay, let's visualize this. Walk us through the encoding algorithm. I've read it, and it sounds complicated, but it's actually surprisingly simple.
It's beautiful in its simplicity, really. You start with your labeled tree. At every step, you look for the leaf node. That's a node with just one connection that has the smallest numerical label.
The smallest number. Got it.
Once you find it, you do two things. One, you write down the label of its parent node, the one it's connected to. That number goes into your sequence.
Okay.
And two, you just remove that leaf node and its connecting edge from the graph.
Yeah.
Then you repeat. Find the new smallest leaf, record its parent, remove it.
And you just keep doing that until what?
Until you're left with just two nodes and one edge between them. At that point, you stop. The list of numbers you wrote down, that's your Prüfer code.
It's so deterministic. The sources gave a great example. For a specific 7-node tree, if you run this process, you end up with the code 14461.
And that 5-digit sequence is the complete unique blueprint of that entire 7-node structure. But here's where it gets really powerful for an engineer.
This is the aha moment.
It is, because that sequence isn't just a blueprint. It's like an X-ray. It instantly tells you how important every node is without you having to do any complex analysis on the graph itself.
You're talking about the degree formula.
Yeah. A node's importance, its degree, which is just the number of connections it has, is encoded right there in the sequence. The formula is unbelievably simple. The degree of any node is just the number of times it appears in the code, plus 1.
Okay, let's test that. The code was 14461. So node 1 shows up twice. So its degree is 2 plus 1, it's 3. Node 4 also appears twice, so it also has a degree of 3.
And node 6 appears once, so its degree is 2. And what about a node that's not in the code, like node 2 or 3?
Well, it appears 0 times, so its degree is 0 plus 1. They must be the leaf nodes.
Exactly. You get instant structural insight. If you're designing a circuit, you immediately know which components are major hubs just by counting numbers. You can flag potential bottlenecks without running a single simulation.
That speed is incredible. But this brings us to the big engineering problem. This all works beautifully for these perfect mathematical trees.
And real-world circuits are anything but.
Exactly. Real circuits are hypergraphs.
That's the chasm we have to cross, right?
Mhm.
In graph theory, an edge connects point A to point B. But on a chip, a single wire, a net, might connect one output to, say, 20 different inputs.
Like a broadcaster sending a signal out to dozens of receivers at once.
Right. And Prüfer's original math just can't handle that kind of multi-terminal connection. It's built for point-to-point.
So how on earth do you translate that octopus structure into something Prüfer can understand?
You use a very clever trick called the star model transformation. The big idea is you change how you think about the circuit. Instead of gates connected by wires, you decide the wires themselves are also nodes.
Wait, so the wires become points on the graph, just like the logic gates.
That's the move. You create what's called a bipartite graph.
Yeah?
You have a set of gate nodes and a set of wire nodes. And the only rule is that an edge can only connect a gate node to a wire node.
I see it. So you take that one wire that connects to 20 inputs.
And you turn it into a central wire node with 20 simple point-to-point edges radiating out to each of the 20 gate nodes.
It looks like a star.
It is a star. And a star is just a specific, very simple type of tree. So you've just decomposed your giant tangled hypergraph into thousands of these simple, manageable little star trees.
And once it's a collection of trees, Prüfer's 1918 bijection is suddenly back on the table.
It's back in play. You can now represent that entire complex circuit blueprint as a single, long, linear sequence of integers.
That translation is the whole ballgame. It's the bridge connecting the two centuries. Okay, so that brings us to the payoff. We've got the code. What does it unlock for engineers in EDA? You mentioned two big areas.
Right. Evolutionary optimization and structural machine learning.
Let's start with optimization, genetic algorithms.
Exactly. We use these algorithms to evolve better chip layouts. Things like designing the clock tree, the heartbeat of the chip, or just minimizing how much wire you need, which saves power.
Now, in the past, if you tried to mutate a circuit design to find a better one, what was the big problem?
The problem was creating illegal offspring. You'd randomly change a connection and accidentally create a closed loop that would just fry the circuit, or you'd disconnect a whole section of logic.
So you'd waste a ton of computing power analyzing designs that were fundamentally broken.
A huge amount. But with Prüfer codes, that problem vanishes. Mutating the design is as simple as changing a number in the sequence, and because of that bijection,
That perfect one-to-one mapping.
every single possible sequence you can create is guaranteed to decode back into a unique, valid tree structure. The algorithm physically cannot explore a broken design,
That's amazing. The sources broke this down into 3 pillars. The first one is validity.
which is what we just said. You're only searching through valid topologies. It makes previously intractable problems totally solvable.
The second is locality. You want small changes to have small effects.
Right. You don't want to change one number and have the entire chip layout scramble itself. Locality means a small tweak to the code results in a small, predictable tweak to the physical tree. It allows for fine-tuning.
And the third pillar is the complete search space.
The bijection guarantees you can explore the entire universe of possible valid designs. You know for a fact that your algorithm isn't missing some hidden optimal solution. You're guaranteed to find the best possible layout.
So it's faster, it's smarter, and it's exhaustive. That's incredible for design. Okay, what about the second big application? Structural machine learning.
This is all about teaching AI to read circuit blueprints.
The fundamental problem there is that AI models, like transformers, they expect a sequence, right? Like a sentence made of words.
They're built for linear data. You can't just feed them a 3D graph of a circuit and expect them to understand it. It's the wrong data format.
But the Prüfer sequence.
The Prüfer sequence solves the interface problem. It turns the spatial graph into a linear sentence. Each number is like a word, and the whole sequence is a sentence that perfectly describes that part of the circuit structure.
And what's the killer prediction this allows an AI to make?
Early prediction of timing violations and routing congestion. the two biggest headaches in chip design.
And how does it do that? Does it just tie back to that degree formula from earlier?
It absolutely does.
Yeah.
The AI model doesn't need to run a simulation. It just reads the input sequence and counts how many times each node's number appears.
And if a number appears a lot,
It's a high fan-out net. It's a major hub. The AI immediately flags it as a potential bottleneck for timing or a hotspot for congestion months before that design would ever be physically simulated. It saves an unbelievable amount of time.
it's fascinating that the engine of our most advanced technology is being optimized by a piece of pure abstract math from over 100 years ago.
It's the ultimate argument for foundational research. We started with this elegant 19th century idea. We had to invent the star model to translate it from modern circuits. And now we're using that genetic code to empower AI and build better chips.
The takeaway here is so clear. These foundational truths are directly solving tomorrow's most complex engineering challenges. It's all about that transformation from a complex, multidimensional system into a clean, linear code.
And we're surrounded by systems like that, systems that are just too complex to grasp all at once.
So we'll leave you with a final thought on that. If finding this hidden genetic sequence was so effective for designing circuits with billions of connections, what other complex systems, from global supply chains to biological protein folding, could be unlocked if we could just find the right way to translate their spatial complexity into a simple linear code?